Okay, so this was the statement we left today. Unproved. And okay, let me write the last part is in the without writing again what is the definition of ES. Okay, so this was the statement, right? And okay. So unfortunately, I don't know. I must apologize because I was planning to cover all the proofs this morning. So basically, these days I'm going 10 pages per lecture. This morning, I don't know why exactly I did 4 pages. Maybe there were less details in these pages, but okay. So I have to apologize. And this also means that at some moment, before this lecture, I had to make a choice what to do and what not. My idea is that I will finish this proof because so there is one rectifiability proof that is complete. And for the rest, okay, I will have to cut something. Okay, so this is it. And I hope it's clear what we are trying to prove. And okay, there was the first step. So now, till some moment, we fix one point in the reduced boundary, and so that's fixed, and let's say it's 0. So the first step in the proof was to show that if I look at how much measured derivative I have in the ball of center 0 and radius r, well, at least for sufficiently small r, this is less than a universal constant times r to the n minus 1. Okay? And universal, okay, usually means that it depends only on the dimension of the space, only on n. Okay, so we proved this. In the proof, actually, we obtained the following. That is that mu bxr, 0r, is less or equal than, up to a constant, hn minus 1, the measure of E intersected the boundary of the ball of radius r. Okay, so there was this kind of argument. This was x, this was E. We would consider this the intersection with the ball of radius r. And essentially, the geometric version was saying that we control the boundary here. Okay, this is not what we did. We did a real proof, right? But what we were trying to say is that we control the boundary here with the boundary here. And again, this is possible only because the set inside here cannot meander around. Otherwise, of course, there cannot be any control of that type. And the reason it cannot go around too much is because we are at a point of the reduced boundary. So in some sense, in fact, this picture is not even precise because essentially this set looks like, this boundary inside looks like flat. So the picture is more like this. Okay, so essentially there will be the normal to this set is essentially constant, which means then that, okay, perhaps here it's more obvious that this part here controls, the area of this part controls the area of this, okay? So that was but of course, okay, the proof is cannot rely on a picture. Okay, so we have now a second step. The second step is that I want to show that there is enough, the set E has enough volume inside the ball, something of the order of r to the n, which again one would say, well, why it cannot be very small? Well, it cannot be very small because then the set should look something like this. Well, but that's not the case, right? I mean, this point should be in the support of the bound of, okay, but again, it has to be proved. In fact, this is probably the most delicate estimate in the entire proof, showing that there is enough volume for E inside. Okay, so what I prove is that if I look at the measure of E inside the ball, well, this is larger than a universal constant, well, positive constant times r to the n for r small. Okay. Actually, I want to say the same also for the complement of it. I mean, this has to be symmetric. I just want to say that there is enough of E, but there is also enough of the complement. Okay, what we know in the limit, there should be half of E and half of the complement. But I'm happy to prove, for the moment, I just prove this. And now C stands for the complement. Okay. And by the way, I will not use it, but from the fact that there is enough volume inside the ball and the isoperimetric inequality, you know that there must be enough surface, or boundary surface in the ball. So you would get that not only this measure is bounded from above by r to the n minus 1, but it's also bounded from below. Okay? We actually don't need it, but it's there. And so we are getting close to the condition that we require in this type of problems, control from above and from below. Okay, so I don't use it, but in some sense it's implicit in this one. Okay, you cannot have this quantity of volume inside without having some boundary, but that's not because of deep reason. That's just isoperimetric inequality. Okay, so actually I will not prove this. The proof of this is the same. You just pass to the complement. Okay, the measured derivative of the set E and the measured derivative of the set E complement are just the same, except a minus sign. So I prove it for this, not for this, but this is okay. So proof, let V of R, the volume of E inside the ball of radius R. And guess what? And now, so this is should be a V. And now by the isoperimetric inequality, we know that this, the volume to the power n minus 1 over n, should be controlled from above up to some constant by the perimeter. Okay, of this set. So I'm applying the isoperimetric inequality to this set here. Okay, so one might wonder, okay, which kind of isoperimetric inequality do we need? We don't care about the optimal constant here, so we need some isoperimetric inequality. How do you prove it? Well, that you can really prove it by approximation. You know, some isoperimetric inequality is true for smooth sets, so it has to be proved to be true for finite perimeter set just by approximation. We do have an approximation results. Okay, so and we are not even talking about the optimal one. Okay, we are just talking about one isoperimetric inequality. Okay, so you have this. But now, what it was written in the proof of this statement was that the boundary, well, what was written, the proof in the statement was written first today in terms of measure, blah, 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 very precise. But the geometric content that I want you to recall is that the boundary of this set is made essentially, the measured derivative, okay, let me call it boundary, is made of this piece, the boundary of B inside, and this piece, okay, the intersection of the boundary of the ball with E. Okay, so it was a precise formulation, which was not true for every R, by the way, it was only proved and is only true for almost every R. But for this one, so we have that here, we have two pieces, the perimeter of E, the perimeter of E inside the ball. So what is that? Is the measure mu inside the just computed in the ball. So this would be this area, okay, plus this one, which already appeared here, that one, Hn minus 1 of E intersected the sphere. Sorry, and this is the ball of radius r, okay? And now we use this fact here, saying that, okay, the measure mu, again, we control with this. So another constant, and okay, I guess as already there is now a remark already used in Yoshi's lecture. Well, this is the derivative of v, okay, of the function v. Okay. Is it true at every r? No, no, no. You have to be careful here. The function v is in W11, if you want, of one variable or absolutely continuous, and this identity, these inequalities are true at almost every point, but not at every r. But okay, let's ignore this step, this detail, and let's keep going. Now we are exactly in the same situation as in the other day's lecture. We have this interesting, well, not the same, actually, simpler, but we have this differential inequality with an exponent less than 1, and there is always a miracle happening there, because what in this case is simpler than in the other one. So we have got this one, okay, and what we do is we take this on the other side. Sorry. Okay, here it was correct. Is it correct there? Yes, sorry. It's the intersection of E with the boundary, and okay, do we agree that this is the derivative? This is the derivative of B, okay? So, of course, if you... Because mu br I control by this. And unfortunately, I decided to use always the constant c, but it's not this. It's not 0. Sorry, this is misleading actually. So it looks like it's 0. It's not 0. It's simply okay. So now quickly, this is 1 over c less or equal than v dot v at 1 over n minus 1, which is the derivative of v 1 over n times n, okay, so 1 over nc less or equal than v to the 1 over n, and now I just integrate derivative. I integrate this from r equals 0 to r equal, well, from rho equals 0 to rho equal 1. So by integration here I get r n over c less or equal than v r to the 1 over n. Minus v at 0, but that's 0, okay? And if you check carefully somewhere, you might realize, well, that you need some regularity of v, otherwise it's not clear why the differential, that's differential inequality is not satisfied everywhere, but almost everywhere. Okay, these are details. And you might want to, that v is always positive, but that's part of the assumption, okay, that we are, we are at least in the support of v. Okay, I mean, otherwise, really, this cannot be in the support of the derivative of E. So, sure, we are close to B. Okay, so this is all we needed, right? Because now we get R to the n. And that was the claim here. Okay, fine. And now we can prove the first statement 4. So we start from that one, that when we blow up the set at the point x, we really get a half plane. Okay, and that's where the first flatness, we get first flatness result. So here we go around all the problems that Tatiana was talking about, that is, how do I get that there is flatness? Because she was trying to derive that by just an assumption on the density. Here we derive it from the geometric property. We blow up the set and we get it's a half plane. And that's all the flatness we need. But that's because the problem is simpler, okay? So you don't get such an easy situation otherwise. Okay, so let me write here the two steps. And the same for the complement. Okay. Okay, so I want to blow up E of the set E at the point, well, x, which is now this point here. It's 0 if you want. Okay, and first things, I want to show that it converges to something. Okay, so I want to show it converges to a very precise half plane. But to begin with, I just show that it converges to something. So that it has a limit up to subsequence. So converge to something in L1 lock and up to subsequence. That's the first result. How do I prove it? Okay, here I use compactness of finite perimeter sets, the compactness theorem, right? How do I use it? I have to show that the measure of this set, that the perimeter of this set inside every ball of radius R, big R, is uniformly bounded in R. So I use this. Inside the ball of radius R, I want to show that this is bounded by a constant. Okay, possibly depending on R. But that's not a problem because of this estimate. Okay, if you look up, the perimeter of this is the same as the perimeter of the original set E inside the ball of radius R, small r, by scaling. And there is a scaling factor which is, guess what, R to the n minus 1. Okay. And now, if we use this estimate here, we get the uniform estimate we need. Because the small r cancel, okay? So we need this, a uniform estimate. We do have it. And so we can apply the compactness theorem. Okay, so this was easy. And so far we have used this, just to make a check. This has been used, yes. Okay, so let me delete it. Okay, E bar, and now I want to say what E bar is. Okay, there is one point. If it is converged to this, I also have the measured derivative converge. But there is one point. When I look at the measured derivative of this inside a ball of radius small r, essentially, and that's the assumptions that we are in a point of the reduced boundary, the normal, the direction, is just almost constant, okay? So what I'm saying is that here, if I look, this is simply my vector, well, up to rescaling, my vector Rx times the rescale measure mu x, Rx, sorry, xr maybe. What I'm saying is that since eta is approximately continuous at x, when I rescale, this goes to a constant. So this means that this must be a measure which is still not, so this would be a measure of this type, but we know that this has to be constant, has to be the approximate limit of eta at x, or at 0, or whatever, okay? So we don't know the measure, but we know that the direction has to be essentially constant. Well, not essentially, it has to be constant. That's exactly the point where we do blow up. From approximate infinitesimal information, we get a constant out of it, okay? And this is the key point, because we are getting a function whose derivative points only in one direction. Now, this function has to be constant in the other direction, and this is not a deep fact. It's just basic definition of distributional derivative. So what I'm saying is that whenever you have a distribution, in fact, whose partial derivative, whose gradient, distributional gradient, is a constant vector times a scalar distribution, that has to be a distribution which is invariant in the other direction, and it's easy to prove. Okay, so this is a statement that it's obvious for smooth function, but it works on a distributional level. In other words, this set here, or this measure here, sorry, this set has to be invariant by translation orthogonal to eta. To eta x. Well, up to 0 Lebesgue set, okay, the usual. So I insist on this. This is a fairly obvious statement for smooth function, but the fact which is important is that it works on the level of distributional derivative, okay? So this is a soft part. It's a soft part, but in some sense is all we wanted to say, because then it has to be, the set E has to be the product of Rn, of a set. So E can be written as a product set of some set contained in E bar. Oh, sorry. Yes, necessary. Okay, so now let's assume, for simplicity, let's call this the fixed sum axis. So n bar x will be the first axis, and here I have the orthogonal direction. nx, eta x, perpendicular. Okay, so I decompose the, then I'm saying that E bar is a set on this line times Rn minus 1. Okay, provided we choose this as the first. So we are left with a set, finite perimeter set in the line. And now the question is, how many finite perimeter sets in the line do you know that have only derivative in one direction? Well, there is not much you can do. You can go up once, and then you never go down. So there is only one finite perimeter set whose measured derivative has constant sign, positive sign. Is empt 0, well, sorry, I'm talking about the characteristic function. The characteristic function has to be 0. Then you can go up once, but you can never go down, because I insist the direction here is constant, means that the derivative of that characteristic function of this set has positive sign. So that's the only possibility. You cannot go down, okay? And so this is giving us, so this is f. F is half line. So we got the half space. Not yet, though, the right half space. Because C, I mean, we have not proven to be 0. But of course, there was a step 2 waiting there. So the basic rules of dramaturgy would tell you that now we have to use it, right? So what I'm saying is that here you have your eta of x. This is the point x where you are blowing up. And somehow it comes out that blowing up, you get as a limit this one. Can it be? Well, no, because if the half plane is too high, means that around this point, I don't see any set E. Well, this contradicts the fact that there is mass. So this contradicts this fact here. Okay? If you look at what this says, this implies then when you go to E bar, and you intersect it with any ball B, you will get at least C R to the n. So there must be mass around inside of E bar inside any ball centered at that point. So certainly the case where your half plane starts up there is not allowed. And using, and in particular, the case where simply E bar is empty, I mean, because this was not, was an option so far, but it's not possible for that reason. And using the other inequality, you say, well, also the case when an E bar starts down here is not allowed. So there is only one possibility. E bar starts exactly here. So let me resume by step 2. E bar is exactly 0 times infinity, which was the half space. Okay? Good. But then we have shown that the limit of our blow up is unique. Okay? So we were, at the beginning, we said, oh, it converges up to subsequence, blah, blah, blah. Well, yes, but the limit is exactly h, and so that limit is unique, not up to subsequence. And by the way, this is also saying that if you blow up the measure derivative, you get, so corollary of this is that blowing up the measure derivative, you get, well, you get hn minus 1 restricted. So the measure derivative of the half plane, what is it? Is this. The measure derivative of on the boundary of hx. No. I took away the direction. I mean, just. So what happens? We got also the uniqueness of the blow up. If you are doing the tangent cone in the sense of price, here you would have added all possible constants. In some sense, here they are not there. Here we have made a blow up with a somehow prescribed without. But okay, this is the uniqueness which we already know it's important. Okay. So we got it. Okay. Okay. End of this part. Fine. And now we prove statement 1. Okay, so we use this. So far we proved statement 4. We proved, well, statement 0 was nothing to prove. There was statement 1. Okay, so but now it's clearly divided into steps somehow. This gives us the nice uniqueness and flatness of the tangent of the blow-up. Well, either of the set or of the measure. In some sense, we get uniqueness and flatness. And now we are going to show how to use this to prove the rectifiability. I think this is the part in Price's work which Tatiana considered easy, and therefore it's but okay. So this is somehow the easy part of that. But maybe, I mean, I don't think it's worth to show, right? Okay. So how comes that using this flatness I can prove rectifiability, at least in this case? But in fact, now the idea I will show now, it works in the more general context. So I will stick to this notation, but in fact it's always the same only proof, that once you have a good tangent and a good blow up, you have rectifiability. Okay? Okay. What information do I get from this? I will not use much information, but there is some information I take out of this, not that much less than what is written here, but that's the key part. And the information I use is the following. Fix, again, a point x. So this is step 1, again, of this proof. Now you take the, that's beautiful. This is, as usual, well, our n of x perpendicular. And now we take, okay, this is the ball of radius r. And now I take a small cylinder here. Okay, so this is not a square, or more precisely, when you go to higher dimension, it's not a cube, it's a cylinder. So this basis is a sphere, and this is a vertical path. So, and this will be r over 5. Okay, and this will be, and the radius of the basis of the cylinder is also r over 5. Okay, and now, since I know that this measure is concentrating along this line uniformly, I know that there must be some mass inside here. Yeah. And I can estimate it. So let's say that in the limit, the mass inside here will be exactly the area of this disk. Well, then if we're not in the limit, for r sufficiently small, it has to be half of this area. So what I'm saying is that the mu of this cylinder has to be at least equal to alpha n minus 1 Rn over 5 to the n. This is exactly the area of the section of this cylinder, of the basis, let's say divided by 2. Okay? In the limit I get this, but at some moment I will get this. So for r sufficiently small. And the other things I obtain is that this part here, the dotted part here, so these two, I don't know how they are called in English. There's not much stuff in there, okay? Because the measure concentrates here. So the measure of the dotted part is less or equal than whatever I choose that scales like, sorry, Rn minus 1, minus 1, minus 1. Anything, I could put anything that goes smaller of Rn minus 1, but I will choose this one. Okay? Now there is only one trick. I'm claiming this, somehow I fixed this to be eta of x. Okay, the trick is that actually what I will really use is that these are also true if instead of eta of x, I use a vector which is close by. So if I twist a little bit the picture, still these are true. I will use it in a second, okay? But okay, so at the moment, all this estimate depends on the choice of eta of x, but I'm saying the same estimate holds if I draw the same picture with a slightly tilted vector, okay? So true also for eta close to eta of x. And that's it. That's all I need from the uniformity. Because then I have the second step of the proof. And the second step of the proof says, okay, so all this holds for every r, so smaller or equal than a certain critical r of x, okay? And the second step of the proof says the following. Now, we take this r of x. Again, I take x here. Now I take this again now this is r of x, exactly the special things there. And then I construct this cone. Okay, this is a double cone. And again, the height here is r of x over 5. And the radius here is r of x over 5. And what I'm claiming is that I'm an asshole. I'm a moron. No, this comes after a suitable selection. Okay, so forget what I said here. So far so good. Okay, what I do now is I split the reduced boundary in two pieces. Okay, and so this is the beginning of step 2. Split the star E into pieces which I called sigma I, with the property that all this property here, or this picture, works for the same vector eta I and for the same threshold Ri. The previous property for every x in this set, the previous property holds for a common Ri and common eta I. So means that suddenly the vector here is an eta I, and this will be an Ri. Can I do that? Well, yes. I mean, I have only to think about it, but it's not complicated. I can partition exactly. So there is no remainder, okay? The union of these sets is exactly the reduced boundary, okay? I have to choose, of course, a lot of Ri, very small Ri, and possibly a very, but this can be done actually with a countable family into countably many pieces. Okay? And then I'm done. Now I work on this. I will show that these are rectifiable, okay? Now, here is the statement. Now you choose a point x in sigma I. You construct the ball of radius Ri. You construct this cone. And now what I'm claiming is that there is no other point of sigma I inside this double cone. So if I take this and I intersect with sigma I, it contains only x. So sigma I somehow has to stay away from this forbidden zone. And I guess you can see somehow why, because by the property I required, there should not be much stuff inside here. Okay? But if I had a point of sigma I around here, sorry, this is 2. This is 2Ri. Over 5. Okay? If there is a point of sigma I around here, then, well, essentially, let me make this has become a mess. Okay, so this is the R over 5. My cone is this one, goes the double. Now, I know that there shouldn't be much mass around here. So this is the dotted zone here. It's almost empty. Well, almost means just in this sense. And what I'm saying is that if I have a point of sigma I here, then I would have the mass coming from this. Okay? And I would have exactly here, and so it would be in the almost empty zone. So there would be a dense part where there shouldn't be. And here is exactly why I put 2. I mean, here 2 was needed, and the 3 is just made chosen so that this is smaller. So there cannot be a point here. Now, you say, well, you have just proved that you cannot have points of sigma I here. But of course, if the points were here, I would simply scale down the picture, and I get a contradiction again. Okay? So there will be no points of sigma I in this set. And now we are finished almost, because then you are saying, okay, we get, so then we get to a situation where you say, well, we have a set which must avoid this. And okay, let me tell you a variant. Let's say that you have a set. So let me let's say you have a set in Rn with the property that with the following property. You have a set sigma with the following property. Whenever I take a point, x, the intersection of sigma with this cone, fixed, is empty, except for x. Let's say you have a set with this property. Okay? So there is a cone C with the property that for every x in sigma, the intersection of sigma with the cone C centered at x is just x. So we have a forbidden zone where we cannot put points of sigma. Do you believe now this is the graph of a Lipschitz function, this set? Okay? Check it out. But simply this means the fact I cannot have point down here means that if I project down here this set and I view at every point here, first it's a function, because I cannot have a point on top of the other. And then I realize that this would be just not intersecting this line. But if I don't intersect the cone, it's a Lipschitz function. Okay, as trivial as it is, this is the basic argument. Okay, you go through Lipschitz function, it's always like that. What I'm saying is that a set of this property is the graph of a Lipschitz function, defined possibly on a subset of Rn, of this. Well, okay, Lipschitz function can be extended, so it is contained in a graph, so it's rectifiable. Now, this set here doesn't have that property because the forbidden area is not a full cone, it's just a piece of a cone. And then I leave it to you to figure out how to make it. So I'm not saying that there is nothing here. I'm just saying that this is forbidden. Yeah, but okay. Think a little bit about it. The set itself will not be a graph necessary of a Lipschitz function because it might contain a point here. but it can be written as a countable union of graph of Lipschitz functions. And you can imagine how. You have to split your set in pieces which are this thick. And then each piece will be a graph of a Lipschitz function. So this is, you need this remark, okay? And this is it, okay? So I've proved that each one of sigma I can be written a countable union of Lipschitz graphs, and therefore the same for sigma, okay? And now, fine. So essentially I proved statement 1. Okay, and now I wonder, okay, what else do we have to prove? Are we finished? Well, I would say we have done most of the work. Let's say we want to prove 2. We should be almost there, but wait a second. So far what do we have? We have that the measure mu is concentrated on the reduced boundary. That was from the beginning. We proved that the reduced boundary is n-1 rectifiable. Do we know then that the measure u is, let's say, absolutely continuous with respect to this? Or do we know it is equal? So in some sense, do we know this? Call this mu prime. One would be tempted to say yes, because would say, well, we perfectly know what are the blow-up of this measure. The blow-up of this measure, I mean, we said it's a rectifiable measure. Sorry, it's the blow-up of a measure associated to a rectifiable set. These are exactly, we proved it a few days ago. When you blow up this measure, you get the Lebesgue measure on the perpendiculars on what? On T of x. So essentially, we have 2 measures, mu and this one, that have the same blow-ups. And one would be tempted to say, well, then of course they are the same. There's one technical point, okay? It's not necessarily the case. You have to be careful on this. So let me it's just a warning. On R, you can find, on the interval 0, 1, you can find a singular measure, which is singular with respect to Lebesgue. Okay? And when you blow it up, when you take the tangent measures, you always get Lebesgue measure up to a constant. So you get a singular measure that when you do the tangent cone, you don't distinguish from Lebesgue measure. So you have to be a bit careful. Okay? So if you think about the tangent cones like the sort of extended notion of derivative, and you would like to say same derivative means same function, well, not exactly. Okay, so first of all, I would like to show this. Do we know this? Okay, and the answer is not yet. But for this, we are almost there. So in principle, what could happen is that this measure lives on this set, yes, but it could be singular with respect to this. Why not? I mean, what tells us that it's not possible? Okay, so could anyone, there is the answer somewhere on the blackboard. Can you spot it? No, you are not allowed to participate. Okay, anybody? Okay, so, right, what? For instance, this one, right? So the fact is that a measure that has this kind of density cannot have a part which is singular with respect to Hausdorff measure. Okay, so that lives on a rectifiable set. Yes, because of step 1. So this is a lemma, in an elementary lemma if you want, but if you have a measure supported on a HD finite set, not rectifiable, that's another matter. such that its d-dimensional density is finite, then it has to be absolutely continuous with respect to HD restricted to the set. Because for not being absolutely continuous, the d-dimensional density would have to be infinite, mu in a set of positive measure. And that's not the case, because actually not only the density is finite at almost every point, it's finite at every point, okay? So you have to be absolutely continuous, first things. Now you can start asking, okay, if it is absolutely continuous, are they the same? And then here we use the blow up. So what we do is that you observe this. So essentially we know, well, you observe this, okay, that mu of bxr, what we proved, is it here, is that this is asymptotically equivalent to alpha n minus 1 r to the n minus 1. Oh, but this is true also for mu prime. So this is for every x in the reduced boundary. Oh, but that's, you know, also for mu prime, because we showed it. That's a property of rectifiable set. Okay, these two things together says that the density of this measure with respect to this is 1. Okay, then they are the same. For HD. So we have proved that they are the same, okay? Same measure. So we proved 0, 1. We proved 2. Actually, I cheated about that, but you might, if you find a mistake, you are welcome. So in what I said, there is a mistake. We can be easily fixed, but okay. I was joking. So no, the mistake is there. If you find it, it would be interesting. Okay, 3. That's somehow hidden in all this part, okay? It's here. So all the rest is here. 4 we proved explicitly. 5, it's a corollary of 4. 6 is the only part we didn't prove. That requires another argument, okay? But that's not, I'm not going to prove that because it's sort of standard argument, okay? So this is the end of the proof of the structure theorem, and I think it's time to take a break, okay? Okay, yes, that's the problem. So, yeah, so when I said this is true, you would like to know that this set is of locally finite measure, which I didn't prove. Well, okay, then in some sense you have a detour and you prove it for the pieces that cover this set. So it's not, I mean, it's an objection to what I said. That's the problem, right? You have to avoid that, but it's a technical fact. So, okay, so 5 minutes. Where is the chairman? Okay. Okay, so let me conclude with some general consideration. Okay, I said at first that you want to use this to prove finite perimeter sets, to prove existence for minimal surfaces. How do you do it? Okay, this is not a stupid question, because in some sense it's not clear where should be. Okay, in finite perimeter minimal surfaces, you would like to find a surface with given boundary. And then I said, what are our nice surfaces in this finite perimeter set theories are the boundaries. Well, okay, boundaries of boundaries are empty. Okay, so in some sense, how does this theory fit the problem of finding surfaces with given boundary? Okay, so that's somehow, it doesn't fit immediately. Let me quickly show how you do it. So the setting So it's not like currents. In the theory of currents, first things you define is the boundary of a current. So it's clear what you have to do. Okay, you fix the boundary, which is defined in lecture 0, and then you go on. Here there is no boundary of the reduced boundary. Okay, there shouldn't be. Okay, because the boundary of the boundary, if anything makes sense, should be 0, empty. Sorry. So how do you do it? Okay, let's put the setting. Imagine that you have smooth, open domain. So this would be the ambient space. Omega, smooth, open domain in Rn. Let's say that, okay, so it's n-dimensional. Let's say that on it, we have, on the boundary of it, we have a subset, which is again smooth, which called, so sigma 0, smooth subset of the boundary. So it has, sigma 0 is codimension 1. Its boundary inside the boundary of omega is this curve which has codimension 2, and that we call gamma. Okay, so this would be our candidate to be the boundary, the given boundary. So the given boundary is this one, is codimension 2, and we are looking for the surface of codimension 1, which minimizes the area among all surfaces with that boundary. So we look for the area minimizing So this is our version of plateau problem. Surface sigma contained in the closure of omega, whose boundary is exactly gamma. Okay, so that's the setting, and the question is how do we translate this into a problem for finite perimeter sets? So this is the setting, and here is the translation. Okay, so this will be gamma, and the surface then will be something like this. This will be the sigma we are looking for. Okay, somehow this is the framework. It's a plateau. It's a problem of plateau type. Okay. Translation in terms of finite perimeter sets. We do something that at first might look strange. Then I will explain why we do it. Okay, so let me take a two-dimensional picture. So this will be gamma. This will be sigma 0. Okay. This will be omega. And now the funny thing is we construct a set outside of omega, which we call E0, whose boundary intersected with the boundary of omega is exactly sigma 0. Okay, and now I give you a problem in terms of finite perimeter set. So find the set E, well, which will be a set of finite perimeter, in Rn, which minimize the perimeter with the constraint that outside of omega, it agrees with E0. Okay? So I'm translating the original problem into this one. And maybe the translation is not accurate, so that's why exactly I'm presenting it as a translation. So I would say that this is a problem. Okay, this is a plateau problem. This is a problem you can easily solve in the framework of finite perimeter set. Are they related? Well, I would say yes, but okay. The relation might be something you are worried about. So this was the original problem. And this is the translation. Okay, so the claim is, well, it's a remark. The second problem has easily a solution. Well, it can be easily solved. That's English, I think this is not, but it can be easily solved in the framework of finite perimeter set. Okay. Why so? Well, because we have all the properties we want. We want to minimize the perimeter. Oh, but the perimeter is lower. Okay, is lower semi-continuous. So the only things we want to have is that compactness. But compactness we proved in the sense that for a minimizing sequence of this set, the perimeter will be clearly bounded. Well, it's minimizing, so certainly will not go to infinity. They are uniformly bounded because they do something inside here, so E will be something. This will be E intersected omega, and together with this will give you the full E. So they are clearly bounded because inside the omega they do whatever they want, but outside omega is just E0. So we can apply the compactness theorem, and okay, semi-continuity and compactness, we get existence of minimizer. Oh yes, we have to check something, whether this condition is closed. Well, we don't write this condition like this. We don't ask that these two sets agree exactly. We ask that we agree up to null sets. Okay, so what we really ask, key point sounds a bit too much, but okay. The constraint which I write in a suitable form is that the measure of the symmetric difference of that as measure 0. Okay, this is a closed constraint. What does it mean? It means that if you have a sequence of set EI which satisfy it and converge in L1, then also the limit will satisfy it, and that's obvious, okay? So there is not a problem, the constraint here. What do you get? Okay, so now one might ask, okay, yes, I get a finite perimeter set. What should be the minimal surface, okay? So give me a surface. Better, give me a varifolds with 0 mean curvature. That's at least, right? If I don't do that, it's really bad. Okay, so here is the minimal surface. So you solve this problem, and now I produce, oh, yeah, this time I was lucky. Okay, so we take E bar to be a minimizer, a solution. Be a solution of 2. And then what do we take as minimal surface? Well, I would start from the reduced boundary of E bar. Well, we decided the reduced boundary is the right object. It is the right replacement for the boundary, right? And, okay, see again this picture. The reduced boundary of E bar will have a part outside, which is the boundary of A0, and then a part inside omega, and that should be our solution. So this is what we expect to be the solution. And it's important that you put the closure here, if you think a bit about it.
E bar is not E closure, but E...
No, sorry, right, bad idea. Sorry, absolutely. It's the optimal. Okay. Of course, in my head, it was very clear that it was not the closure. Okay. Now, what can you prove easily? Well, the first thing you can prove. This is indeed the varifold associated to this set. Okay, this is rectifiable because it's a piece of a rectifiable set. Okay. Second, the varifold associated to this has zero mean curvature inside omega. So, the varifold has zero mean curvature. So it's stationary as a varifold in omega, okay? What does it mean is that when you check the definition of mean curvature, we plug in vector fields which are with compact supports in omega. So they don't see the boundary, because this should have a boundary, right? So this is the picture. Here is the points is your curve gamma. Here is E0. Your set will have something like this. It might actually, so this will be, it might actually touch the boundary. It's not forbidden. So this is E intersected omega bar. And this part here is and this is sigma. So a part of the boundary of sigma can be on the boundary of omega, but the part inside is mean curvature. Okay, so the part that touches the boundary, unfortunately, you don't know, but of course, I mean, I would be solving an obstacle problem, so I can't expect mean curvature equation to hold. That's not natural. Okay, so here it is, and the proof is easy in some sense because we did all the computation already. Okay, you take the first variation of this, of the area of this, I said, okay, I mean, I didn't say it, but at some moment maybe it was said. The computation of the first variation, as long as you don't do integration by parts, it works for every rectifiable sets, because the area formula, which we used to compute, it works for rectifiable sets as well. So the computation I did in the first lecture works, and as Yoshi reminded you, I think more than once, it works in every case. So this will be the integral over sigma tilde of a vector field, the initial velocity v. Sorry, the divergence, tangential divergence of the initial velocity v. Okay, so that exists, and that formula doesn't require any regularity on sigma tilde. Only when you want to pass to the integrate by parts is you will require regularity. But this part is exactly the point of all the definition. But on the other hand, what is this?
No, sorry, okay.
No, I think. Sorry. But what is this? Well, this is exactly the reduced boundary of the deformation of E. So this is the same of the perimeter, sorry, of the perimeter of ET. Okay, this is not the full boundary, but the part outside doesn't move at all. So whether I add or not the part outside, when I compute the derivative, I'm changing by a constant. So these two are the same, because these two functions are the same up to a constant, which is the part of the reduced boundary of E, which is outside omega, that is in an open set. They are, okay, you have to be careful, but they differ by a constant. And this has to be larger or equal to 0 by minimality. And then you change your vector field and you get 0. Okay, so we do get a varifold with 0 mean curvature inside. Okay? So, and then the question could be, in which sense, so this is the first question, in which sense we get a minimal surface? Well, at least in this sense. And then the second question, okay, in which sense this surface has the right boundary? Okay, in some weak sense, of course. Okay, that's not. And okay, what it could be? Well, if you know currents, so the answer would be very nice in the sense that this is a rectifiable set with integral multiplicity. It has an orientation. It comes from the inner normal. So indeed, it's an oriented rectifiable set. You can talk about currents associated with it, sort of generalized surface. But for this generalized surfaces, there is a very well distributional notion of boundary. So you don't need any regularity for that. And the boundary of it is exactly gamma. So first answer is that the boundary of the current associated to sigma bar is gamma. In dimension 3, I mean, this means that Stokes' formula holds. You can prove this, that is, if you integrate over gamma a vector field, smooth, compactly supported in Rn. So you take the work of the vector field, and then you get the same as integrating the flux over sigma of the curl of V. Okay, for every V smooth vector field on Rn. Okay, so in this weak sense, it is the right boundary. It is the boundary, okay? You can say more if you want, but it amounts to the same. You can observe that, well, gamma was defined to be the boundary of this. Then, if you want, it's also the boundary of this. Okay, actually that can be made in a very sense because you could choose the set E0 very regular. So gamma is the boundary of this surface in a very regular sense. And now you notice that this piece of the surface and this one together form a boundary. So in some sense, they're different. They should have the same boundary. So you are sure that the boundary of this is gamma. Well, then, if putting together these two surfaces, there should be no boundary because they are a boundary. You would say the boundary of this is gamma as well with the right orientation, but I'm not one to enter into this, okay? So it spans the given boundary with the required regularity, okay? Okay, few seconds just to say one remark. Why do I do something so cumbersome? Adding a set outside, blah, blah, blah. Couldn't I do something simpler? That is, why not solving the problem, simply you take this is your gamma, this is your sigma 0. Okay, I'm telling this because someone already asked this question, so perhaps it's better to answer it. Okay, I mean, it sounds a bit strange, right, to set it up that way. Why would I do that? So one would say, well, the easy way to do it is to simply say minimize the perimeter of E among all finite perimeter sets E such that, contained in omega, such that the reduced boundary of E intersected with the boundary of omega is sigma 0. So you would consider these sets. And then you say, okay, I fixed, how do I constrain my, so how do I, which kind of boundary constraint do I put? And simply say, well, I consider all sets E such that the reduced boundary intersected the boundary of omega, so this part here should agrees with sigma 0. Why not set in this problem, which seems a little bit simpler than the other one, more natural, I would say. What's wrong with this? So this is the question mark goes with why not. No, you require that this set up to an H1 null set agrees with this set. So you just require that they are the same set up to an H, maybe an Hn minus 1 null set. Okay, as before, if you want to set it up in the right setting, you cannot ask identity of sets. You have to be a bit more careful. So what's wrong with this? Any guess?
So if you don't do this inclusion, then if omega is if the rest of the boundary of omega is the minimal surface, then you have an issue.
Sorry, no, say that again.
So if the rest of the boundary of omega,
So this part here,
yes, is the minimal surface.
why?
Well, assuming you have your omega, you start with some omega, right?
No, the omega is given, okay. The ambient space, this is omega, the ambient space is fixed.
Assuming this is the minimal surface.
Okay, yeah, you would get that, but it wouldn't be so wrong.
Yeah, but the equality
Huh? No. You would have simply that the surface I do as before. So my sigma in the end will be, okay, I take the minimizer E bar and set sigma bar, my candidate minimal surface, to be the boundary of E bar minus, as before, sigma 0. Now, this I would take. In this case, I would simply say, yes, the minimal surface is this. It's not a priori that bad. It could be, if I've chosen the wrong.
I think you don't have compactness.
Yes. This constraint, no matter which way you write it, it's not closed. Not a closed constraint. So it's a technical issue. It's not a philosophical, it's not a deep one, okay? It's not a closed constraint. And the reason is, well, is this picture, why it's not closed, because you can have a sequence of sets of finite perimeter, which, like this one, where this is a sequence of sets EI, the thickness E epsilon, the thickness is epsilon. As epsilon goes to 0, the limit of the sets will be the empty set. So all the sets you start with have the right trace on the boundary, but the limit doesn't. So you get out of all the sets you start with satisfies this constraint, but the limit set doesn't. You don't have compactness, okay? And then the word trace should give me away. The problem is that we are working with BV function, and the trace operator for BV function, so the trace on the boundary, is something well defined, but it's not semi-continuous with respect to the weak topologies you would like to use, okay? So this is a problem of the lack of continuity of the trace operator for BV function. For Sobolev function, the trace operator is nicely continuous. For BV, it's not. So there is this phenomenon. By the way, it's real, okay? If you have two planes parallel and you put two disks on the side of the plane. Okay. So your boundary is this one. Okay. If the planes are close enough, the minimal surface will be this. But when they get far away, the minimal surface will become this, simply the two disks. Because it's not convenient to bridge in the middle anymore. Okay. And then you realize immediately that if you set the problem in this way, you get something wrong. You get the empty set as an answer, exactly because the minimizing sequence will be some sort of bulbs here that's flattened towards the disk. So you get the wrong answer. Okay. While that way, you get the right answer, so to speak. Okay. So this is a. Okay. There are problems related to the minimal surface equation that it doesn't touch. Okay. Yeah, I'm finished.
Maybe you can say a few words about where this theory goes. Because I saw that there's, for example, a Olympic book by Maggie.
Yes. Okay, good answer, good question. Okay, so this is it, and this was the end of it. Where does the theory goes? Okay, very quickly then. First of all, producing minimal surfaces this way, you can do it, fine. It's not really the perfect tool for that. For instance, in certain cases, you don't get an answer. So let's say that your ambient omega is a torus, and you want to find the minimal surface with this boundary. That you don't get. And you don't get because this is not the boundary of anything inside the torus. Okay? So there is a perfect minimal surface, is this here, and you don't get it in this framework. So watch out. You get it in the framework of currents, but you don't get it here. So this is not. Finite perimeter sets are not a perfect theory to get in minimal surfaces. They provide an answer, but not always. They are a perfect tool to set up the so-called capillarity problem. Problems involving, let's say, drops of water, to tell the story in a accessible language, where the energy is the surface energy, and so on. There they are perfect, in some sense, because you start from sets from the beginning, not from surfaces. Here is artificial, in the plateau problem, that we want to talk about surfaces, but instead we talk about sets of full dimension. Okay, and then, for instance, one thing you can use this theory for, because of its compactness property, is to give an easy proof of the weakest of the statement about approximation of the area that Yoshi mentioned. So you minimize. So this is, for instance, a place where you find out that this is somehow useful. So let's say you fix omega, and you minimize this energy functional. The one which was mentioned today and yesterday. And maybe to have a non-trivial minimum, so we are not talking about equilibrium point, we talk about minimizer, so we don't get zero or constant. You add a volume constraint. So you fix the average of u over omega to be some constant between -1 and 1. Okay, so you get a non-trivial minimum, and you would like to say that the minimizer, u epsilon, converge to a function we take only values 1 and -1, and the boundary, the interface, is a minimal surface. Okay, that's for minimizer. He said this is the easy result that Giovanni is going to show you, and okay, things went in a slightly different way. I'm sorry, that was the original plan. Because what I wanted to say, the kind of result he has been showing are much deeper than this one about minimizer, but there is one, and complicated in some sense, because it couldn't be otherwise. But if you want to prove only this, that is u epsilon, so that for minimizer, let's say the varifold associated to u epsilon converge to mean curvature varifold, or if you well, that's not correct. Let's say you want to show that this converge to a function well, it converges to a function we take the values 1 and -1, okay, not 1 and 0, so in this sense. And then what you show is that what you can easily show is that this set E minimizes the following, the perimeter of E. Okay, among all set which satisfies the same constraint here. Something like that. Okay, so this means, okay, this is easy to prove using finite perimeter sets and the notion of gamma convergence. But you know, I mean, if I say like this, sounds like a complicated story, but it's really simple. Of course, it's not a powerful thing, but it's a result that can be proved in half an hour. Okay, and so you get out of these minimizers a minimizer of this, which is an area problem in some sense. Okay, and this is naturally set in terms of perimeter, for instance. And there, the key point in all the proof, one of the things that you cannot work without is the fact that you have compactness of finite perimeter sets. Nothing else. That's what the proof relies on. Of course, the results is weak, because the only things you know is the convergence in L1, or L2, whatever, but is not the kind of, and nothing, you cannot say anything about convergence of critical points. That's the hard part, okay? But for minimizer, there is an easy theory, and this easy theory is based on the essential way on the fact that you have finite perimeter sets. I don't know whether this answer, then there has been other application of these finite perimeter sets, essentially in a situation where providing an easy existence result was priority compared to providing regularity. But the big book of magic contains also the regularity theory, okay? It says that the surface you obtain, the sigma tilde that you obtain here, in the end agrees in dimension less than 8 of the ambient space, in dimension less than 7 of the ambient space, it agrees with a smooth analytic, with an analytic surface. And you start having some singularity in dimension 8 and the singularity of codimension 7 in the surface. So there is a regularity theory, but that's why the big book of magic is a big book, because there is the full regularity theory inside, okay? So that's where the theory goes if you want regularity, but that's more complicated than all this. So I did the soft part of all this stuff. Okay, the hard part is to prove regularity, and that requires a book, yes. More question, I would say. Oh, yes.